Alright, so let's put this into OneNote in the other place, and we'll get started. Alright, add another page. I'm going to do something here. I don't need this. Alright, so let me clip it. I guess it's here, right? And here. And insert screen clipping. Okay, and then I'll take the second part too. Clipping. Alright, so other people who are not in on this discussion for this problem, here you have a vector space of polynomials of degree n or less. Oh dear, is this not working? Oh, here we go. Of degree n or less, and the derivative is an operator, and it says find the matrix of the derivative operator in this order, this basis for the domain, and the basis f for the codomain, and determine if this derivative operator is diagonalizable. All right. So let's see. So one approach I suggested is if you can't. So I think the question is now on this: determine if the derivative operator is diagonalizable. One thing is that if you can't solve in general, do a specific example. Always work your way up from simple to more complicated. So let's try n equal 2. Okay. So the question is, what is this operator in this basis? And how do you find out what that is? What's the matrix in this basis? So that means that E equals, well, let's see, well, just try n equal 1. Sorry, n equal 1 is going to be the 2 by 2. So your basis E is going to be 1 and t, and your basis f is going to be t and 1, and your operator is p of x goes to the derivative of p of x. Alright, so what's the matrix? And how do you find it? Oops, sorry. You still with me? What do you mean the derivative of E? Well, E is a basis. These are two different vectors. You can only take the derivative of a vector one at a time. Yeah, but you don't take the derivative of a set. I think what you mean is the derivative of 1 is 0, and the derivative of t, actually I should say, I have an x and a t here. Does he use x or t? He uses t, so I better get rid of my x's. My bad. Alright, but we're not looking at that. We're only looking at one dimension, right? We're only looking at one dimension at this point. I mean, a 2 by 2 matrix. I mean, I assume you already did that for the other problem, but we're focusing in on this case, right? So d1 dt is 0. Whoops. d1 dt and dt dt is equal to 1. All right. So what you have to do now is write this in the f basis. So you have to write this as a linear combination of the two f vectors, which are t and 1. And this is also a linear combination of two of the f vectors, something times t plus something times 1. All right. So what are the coefficients? Or you can just jump in and tell me what the matrix is. Okay. All right. 0 and 1. Okay. So what's the matrix? Okay. All right. So we can see if we can verify that 0, 0, 0, 1. All right. Now if I multiply that by, so let's check. If I take 0, 0, 0, 1 times AB, I'm going to get 0B, and that expresses the fact this AB represents A times 1 plus B times T, and this 0B is in the F basis. This is in the E basis, and this is in the F basis. So this should be equal to 0b, which is going to be 0 times t plus b, which looks good. Okay, so I agree. All right, so is this matrix diagonalizable? Don't all speak at once. Now, if you don't remember, if you don't, okay. Well, all right. So Amanda said she doesn't think it is. Okay. All right. So I mean, the way to do this is you can go ahead from scratch to find the eigenvectors. Just just go ahead from scratch. Right? So if you have A is equal to 0, 0, 0, 1. Okay. So to find the eigenvectors, what do you do? Well, you can do that. I mean, you can go ahead and do that, or you or we can just start from scratch the general method of finding eigenvectors. And that's correct, right? A minus lambda I is equal to minus lambda 1 minus lambda 0, 0. Okay, and then what's the determinant? Yes. What's the determinant? Okay, negative lambda plus lambda squared. I'll buy that. And what are the roots? I mean, this procedure should just be kind of something you can do in your sleep. Yeah, 0 and 1. Okay, so these are the possible eigenvalues. Okay, so let's look at first is lambda equals 0. So that's going to be, that just gives us A. So that's going to be, so if we have to solve AX equals 0x. And so here we have A is 0, 0, 0, 1 times X equals 0, 0. Okay, homogeneous equation. What's the general solution? And again, this is just automatic. There's, I mean, you should just plug this in, put this into your meat grinder and grind it. We've done the same thing. Really, we've done the same thing dozens of times. What's the general solution? How do you find the general solution of a homogeneous equation? What are the magic 4 letters? RREF. Okay, what's the RREF? Just row swap that thing, yes. Okay. Maybe, you know, I'm really thinking that I'm not going to go any farther. This is just a problem of turning the crank. And I think you know how to turn the crank. You have to find two eigenvectors. If you can find two linearly independent eigenvectors, then the matrix is diagonalizable. So I just say continue. Now, if you want to do it on your own, that's fine. I'll listen. But I don't. I think it's not. At this point, this is something that I can kind of, according to my judgment, you should be able to do without me working through the steps. Okay. Right. Yeah, I know it's hard to switch, but that's what I would say here. Now this only works for 2 by 2. I'm trying to think what I would say for once you do 2 by 2. Well, I kind of have to see the result for 2 by 2 to see where you go from there. If it's not diagonalizable, then really you're done. If it is diagonalizable, maybe you can look at 3 by 3 and see what is going on. Now I do want to say one thing. They do some funny things with these bases, right? So in this exercise, they use the domain basis. E is unequal to the range basis. To the codomain basis. Okay. Now, my question is, it's much easier to do both domain and range in the same basis. Okay, so let's see. So I'm going to say something. I'll say let M equal the matrix with domain E and codomain F, and let M prime be the matrix with domain E and codomain E. So my question is, what is the relationship between these two matrices? Oh, you can you see my screen? Can you see my screen? Can you see my screen? Okay. Yeah, just tell me to repeat and I'll just have to repeat. Okay. You know what? I think this is not working out how I thought it was going to work out, so I think I'm going to scratch this question. I think I'm not going to yeah, I'm going to scratch this question. Never mind. I thought something would work out. I think this would be useful, but I'm going to scratch this question. But I will say that you can certainly do that. So I would look at 2 by 2. So I would look at 2 by 2, 3 by 3, 4 by 4, and see if you can find any regularity in the eigenvectors. That's what I would do. So let me let you work on that, and I'm sure you'll be able to do that. Confident in your collective ability to solve that problem. So let me go up here and erase this and destroy the evidence, so that yeah, I thought that might be a useful thing to do, but it turns out it's not going to be so useful. So we'll get rid of that. All right, question 7. All right, let me take a look. Okay, right. Yeah, I think I just said first do the first 2 bullets. Yeah, it is somewhat similar, isn't it? Now I think what's confusing about this is he's using lambda here for a constant, but it's not necessarily the case that lambda is the eigenvalue. So instead of writing lambda 1 0 lambda, you might want to write a1 0 a. Something like that. But yeah, I think you can solve that. You can do that the same way. You can do that the same way. And also, if you have trouble with arbitrary constants, put in a specific constant. Like you can put in 1 or 2. So I just want to encourage you to try those things. What you want to do is, if you can't solve a bigger problem, you go break it down into baby steps and see if that gives you some idea. If you can't scale the cliff, you try to go around back and see if there's a back way up. In fact, I can find, looking at these 3 matrices, I can find one eigenvector right away. I can see one eigenvector right away. I don't know if you can see it, but in all these cases there's one eigenvector that's very evident to me. And I think what do you mean 1? 1 is not a vector. I mean, do you mean the vector of all ones?
Sorry, I was thinking of Eigenvalues.
For this one, are you looking at problem 7?
Yeah.
Yeah. Well, as I mentioned, if you replace this lambda with A and solve for the eigenvalues, so that would be A1, 0A. If you have that matrix and you solve for the eigenvalues, what are you going to get?
When we were working on this one in class last week, we figured out that lambda was just lambda.
Yeah, it turns out that lambda is the eigenvalue, yes. But do you get the point that I'm making today? That's not immediately clear. You actually have to work that out. But you can go from there. If lambda is the eigenvalue, then what are the eigenvectors? Okay, 1, 0 is the eigenvector. Certainly that works, because if I take this matrix times 1, 0, I get lambda 0. So can you give me an eigenvector for this one? The 3 by 3?
Isn't it 1, 0, 0?
Yeah, 1, 0, 0 does the same thing. And then how about this one? One with all zeros. Okay, so, but that's one eigenvector. That's certainly not all the eigenvectors, but that's one eigenvector.
Well, you have to multiply it by the k constant.
I'm not sure what you mean. Well, yes, the eigenvector is just the vector. 1, 0 is an eigenvector, 2, 0 is an eigenvector, and so on. You don't have to be too careful about that. 1, 0 is an eigenvector, 2, 0 is an eigenvector. Those are both correct answers. But that doesn't give me a set of, like for instance this matrix, that doesn't give me a set of 2 eigenvectors.
This goes back to that question that probably were discussed before. Eigenvalues equal to eigenvectors.
That's not true. Not true, not true, not true. You can't conclude that automatically, no. The identity only has one eigenvalue, but it has many eigenvectors. What you have to do, turn the crank, find the eigenvectors. That's what you have to do. So what do you see? Or should? Okay, all right. Okay. This is one of the things you definitely need to write down. You can't just see this in your head. So I hope you all are sitting there with pencil and paper. Find the eigenvectors.
So if the eigenvalue is lambda,
Yes.
then any vector with one constant is serves as an eigenvector in this situation.
Okay. So that's one eigenvector. Are there any others? Are there? That's certainly not. Those are not linearly independent. Are there any others that are linear?
I mean, but they're an infinite number.
Okay. All right. But that's. But there's always an infinite number. But are they linearly independent?
They're not.
They're not. Can you find two linearly independent eigenvectors? Are there two linearly independent eigenvectors? No. Okay. So what's your answer about diagonalizable?
Then you can't diagonalize
Can't.
because you must have an linearly independent eigenvector.
That's right. That's right. So the missing step is you need to show me that there's only one linearly independent eigenvector, and that's the old REF stuff. Take the matrix, subtract the eigenvalue in the diagonal, take the REF, find the solution. And since there's only one eigenvalue, you only have to do that once.
The reason there are an infinite number of eigenvectors is because if you take multiple of an eigenvector times a matrix is equal to a multiple of the eigenvalue times
Yeah. I can say that the way you say it is that any multiple of an eigenvector, yes, and I'll be a bit more specific with eigenvalue. Let's just say lambda is also an eigenvector with the same eigenvalue. Okay, so I just do an example. If you have m times v equals lambda v, then if I multiply v by a constant, well, that's the same as c times mv, right? Because I can pull the c out, and mv is lambda v, so that's c times lambda v, and that's the same as lambda of cv. So that means that m times cv equals lambda times cv. So that means that cv is also an eigenvector. Okay, with eigenvalue lambda. Okay. So I think, as I was telling Amanda, if you say, give me an eigenvector, or give me a linearly independent set of eigenvectors, I could choose 1, 0, or 2, 0, or 7, 0. It really doesn't matter. Any one of those is equivalent, because I could get any other one from any one of them. So should we move on? Yeah, maybe we should move on, because I don't want to spend the whole time online this time. I just want to give you some indications and take you to the point where I think that you can work it out yourself. What other problems do we? Yeah.
Can I ask one last question before we move on?
Sure.
So what I'm understanding you saying is, if I find an eigenvector,
Mm-hmm.
and let's say in the case of a 2 by 2,
Right.
I find one eigenvector that, so all others are purely dependent upon that one eigenvector, then since there's only one for 2 by 2, then I can say it's not diagonalizable.
That's right. If you can show there are not two linearly independent ones, then it's not diagonalizable. That's what you want. You want to get a basis of eigenvectors, and we know that with 2 dimensions, your basis has to have 2 vectors. That's something we know. So if you can't make a basis, you can't diagonalize it. That's kind of the way you can think about it. Okay. All right. Go ahead. Problem number 2. So let me see if I can say something. Oh, it's not rendered anymore. Okay. Okay. So here it says, write the matrix P for the change of basis from S to the standard basis E1, E2, E3 of R3. So what are you thinking here?
Well, I was thinking it went with what you had done in the YouTube videos, where it was you had to go the back route.
Okay. Okay.
Unless I'm thinking of something different.
Well, let me see. We certainly did talk about this. So I think, and we talked about it in class too, I think. So let's look at the OneNote. Where did I put that? Did I put that under chapter 13?
I can't remember.
I think I did. All right, there's the outline. This is going to be, because I remember drawing that diagram, or I think maybe it's here. Okay, yeah, here, this looks like something. Okay, in fact, it looks to me like this is exactly the situation we're looking at. Let's zoom in.
Yeah, that was from the YouTube video.
Right, right. So this is on the OneNote page. So you're changing from the V1, V2 basis to the E1, E2 basis. So that's this case here. So here's your change of basis matrix. So just figure out how to get that from the basis vectors, and you're good. How did this matrix arise from the basis vectors? I think that's the question you need to ask yourself. So, well, maybe I should ask you, Amanda, how are you thinking that comes from the basis vectors?
Well, because we have to. It's kind of hard to explain. Because, like in the YouTube video, we made it go backwards. We had to take a different route.
Well, but look at this. But it's not asking about. I think it's exactly the situation I'm showing on the screen. You have a it's asking for a change of basis matrix. You have one basis here, and you have the standard basis here. So it's no more complicated than just this. You're not trying to change a linear transformation from one basis to another. You're just trying to change the basis. So I think you may be making this too complicated. Well, there's any number of ways to do a problem wrong. So that's natural. But really, just look at this. Maybe that's a good enough hint. Is that just stare at this situation and apply the same situation to the problem you have here. Because here it's saying change a basis from S to standard basis, and that's just what I have here. Change a basis from V to standard basis, and the matrix is here, and this matrix can be obtained using the basis vectors v1, v2, and he gave you the basis vectors here, so it should be pretty much apply the same thing here that was applied in the OneNote. So just follow it through, just follow the logic through. That's how you would think about it. Here you have a linear combination of vectors. The vectors are f1 through fm, right? You have a linear combination of vectors, and the coefficients are these m's. Right? So you can write that this way, as the matrix formed by the columns times this vector here. So this linear combination, expressed in the f basis, is this column vector. This column vector expresses the information in this linear combination. Let me see if there's a way that he does this more explicitly. All right, so here, look at here, has L of AB equals this matrix times AB. Now, where did the AB come from? The AB came from here. Actually, this is wrong. It should be A plus B times T. Or no, I'm sorry. No, it came from here. Sorry, this is right. A plus B times T. The AB came from here. This A plus B times T in this basis 1T is AB. If you want to express the vector A plus BT in the basis 1T, these are the coefficients, AB. All right, let's see if I can find a better example. I thought there were several examples in the book about that, but maybe I'm wrong. That's what the... Well, I have in my OneNote. I certainly have that in my OneNote. Yes. Yes. Yes, yes. The coefficients in this basis, the coefficients give you the column vector. So the other question is, what is x in the standard basis? How would you express this vector x in the standard basis? No, because what you've done is you've changed the vectors. You've replaced this vector with another vector. I think it's important to realize that this basis vector here in the standard basis is these values. So in fact, this first vector in the standard basis is minus 1 over root 2, 1 over root 3, 1 over root 6. This whole calculation gives me x in the standard basis. So this right-hand side is x in the standard basis. That's what it's doing. Now I suggest you watch the video again. Yeah. Yeah, I think you have to watch the video again because I talk about this. Maybe when you guys rewrite this book, maybe you can make the point more clear. But no, Aaron and Adam are going to do something for me. Well, I would just suggest you watch the video again, because I'm really just going over this very same point. I'm going over the very same argument that I did in this Okay. Well, the point is that x in the standard basis is equal to some matrix times this ABC. And this some matrix is the change of basis. Okay. And I can say also that this whole deal here, this is the vector x in the standard basis. When you write down a vector in components, that's what's called the standard basis. Is that when you write down a vector in components, you're assuming that those components are in the standard basis. What did you say, Adam? Well, that's what I would say. Okay, well then there's something wrong with the problem, because that's not correct. That is incorrect. The correct answer is just. Okay. Okay. Yeah, it's wrong.
Well, maybe it actually has like the variable switched up.
No, it's just wrong. It's just flat out wrong. Yeah.
Because I just tried it. What Adam is saying is correct. Inputting like what because I have 10 set of numbers. Inputting your first and the first row.
Yes.
Vector.
Yes.
And that's wrong.
Yes, it's just wrong. Yes. Well, that's interesting because actually I know how to fix this problem. Yes. Yes, that's correct. They have reversed these questions. That's what they've done. They've reversed the questions. That's the problem. In fact, that is true. You can find that in the book. Yeah, you can find that in the book. And in fact, it's not too difficult to show, because it follows from the fact that the vectors are orthonormal. Maybe you can even see that if you write this. If you take this, suppose you take this vector here, right? This first column vector. Let me zoom in. Right. Now suppose I take this vector and I take the inner product with itself. What's the answer going to be? Or the dot product? Yeah, in fact you didn't even need to work it out. That's what orthonormal means, right? Normal means that the length is 1. On the other hand, suppose you take the inner product of this one with another one of these vectors. What are you going to get? You get 0. That's right. Now if you remember, when you have matrix multiplication, basically matrix multiplication involves inner products between the rows and the columns. Right? If I get the 1, 1 entry of a product, that's the first row of the first matrix times the first column of the second matrix. If I get the 2, 3 entry of the product, that's the second row of the first matrix times the third column of the second matrix. According to what we just said, if you have orthonormal vectors, the inner products are always going to be equal unless you're taking unless the two vectors are the same. So you can think about that, but that argument shows that in fact the transpose of this matrix is the change of basis matrix in the other direction. Okay. So I'm not sure what I'm going to do about that. Yes, I guess that's the best solution. Is I'm just going to have to send out an email that those two are reversed. Yes, yes, yes. Maybe what I should do is I should just rewrite the problem. I'll have to figure out how to do that. Well, no, I say write the matrix P inverse, P for the change of basis from the standard basis to the basis S. Well, because I loaded this from the book, not from the WebWorks site. So these problems are all within my own. I have control over these problems, I believe. I think. I'll have to check. That's one thing that maybe Adam and Aaron can help me with. Getting around this WebWork thing. It would be nice if we could fix some of these problems.
Make them so that they don't have square root of 2,479.
Well, come on, Aaron. This is real life. I mean, you got. The answer is not always 2. Oh, 42. Okay, for mathematicians it's 17. For hitchhikers it's 42. For mathematicians it's 17. Well, there was a famous math summer camp where there was something supposed to be something mysterious and special about 17. It's a very well-known summer camp. A lot of well-known mathematicians went there. I think if you Google yellow pig 17, you may find some information. Yellow pig 17. Yeah, I think there should be something online about that. Actually, I haven't tried that in a while. Maybe I'll look now. Yeah, this I guess you do something here.
I went to the first one and I'm actually reading it now.
I shouldn't have gotten you off on this.
We all need a brain break.
Well,
We're still learning that.
yeah.
My brain hurts.
Well, yeah, the problem is, of course, that for graduate classes, you really want to have these long sessions, so you don't have to travel. But of course, if it were online, it really doesn't matter as much. I suppose in the coming semester, we'll just have two online sessions like this, and that should be fine. Then you don't have to for abstract algebra. Yeah, because I don't see, if we're online, there's really no need to spend a marathon session. It's just another night. It's just another night of the week that I won't sleep. That's all. That's all right. I'm actually doing pretty well.
You're using the same book that Kat sent us?
Yes. Yes. But yeah, you might want to look at the earlier chapters there because really, well, I think I'll have to do a lightning review of the first several chapters, but the focus is going to be on the chapters beginning, basically beginning with chapter 9. Well, we'll do a lightning review of the other ones. So if you're that might be a good winter break reading, because I'm not going to. I mean, we'll do basically 2, 3, 4, 5. Well, I probably spend some more time on cryptography. So we'll spend some time on cryptography because I think that's a good application. But 1, 2, 3, 4, 5, and 7, we won't spend more than 2 weeks on all of those chapters together. Well, the sigma notation, that's something that you're supposed to know as an undergraduate anyway. How to write sums as sigmas. No, polynomials we'll do a little bit on that. We'll do some of the later stuff. Because well, I think you must have, in calculus, you must have seen sigma notation. Yeah. Well, if I do some of this stuff, I suppose if I do some of this stuff more in depth, I would spend more time on it. So I'll think about this. I may spend a little bit more time on some of these parts. Like chapter 6, I think some of the later stuff is nice to look at if you haven't seen it before. Oh yeah, if I do that, then we'll spend some time on that. But most likely I won't end up doing that because there's not enough time to do some of the more important stuff later on. But the big thing next semester are the symmetries, permutations, abstract groups, further cryptography, equivalence relation, coset and factor groups, and then this error. I would like to do this one, the error correcting codes. I would like to do that, and that's probably what we're going to spend most of the time on. But it's a lot of pages, but this book is not dense. It's very there are lots of examples and it's kind of drawn out. All right, so I guess we're done with questions for today. I'll see what I can do about fixing that problem. Thanks, Adam, for pointing that out. So I think we're good for today. I'm going to stop the recording.